You have noticed something. Maybe you noticed it gradually. So gradually you almost missed it. That a name takes a moment longer to retrieve than it used to. That you walk into a room and the reason you came in dissolves before you can catch it. That a sentence you were midway through just goes. You probably told yourself it was stress, or sleep deprivation, or just being busy. And it might be all of those things. But there is something else happening that none of those explanations account for. Something biological, measurable, and specific. In January 2026, researchers at the University of Cambridge published findings from MRI scans of 10,173 women. What they found was not vague, it was precise. And it explains exactly what you have been feeling. There are 4 specific changes that begin happening in the female brain from your mid to late 30s onward. 4 changes with named brain structures, named mechanisms, and named researchers behind them. And here is the most important thing I can tell you before we get into what those changes are. None of them are inevitable. All of them are modifiable. But you cannot modify something you do not understand. So this video is the understanding. The Cambridge study identified 3 specific brain regions, where gray matter volume was measurably lower in postmenopausal women compared to premenopausal women of similar age and health. The hippocampus, the entorhinal cortex, and the anterior cingulate cortex. Here is what each of those regions does in plain language. The hippocampus is your brain's primary memory formation and retrieval structure. It is where new experiences get encoded into long-term memory. It is also where spatial navigation lives. When hippocampal volume decreases, the first things you notice are exactly what you have already noticed. Slower name retrieval, moments of forgetting why you walked into a room, the sense that short-term memory is less reliable than it once was. The entorhinal cortex is the gateway between your hippocampus and the rest of your brain. It controls what information gets passed to the hippocampus for storage and what gets retrieved from it when you need it. When it shrinks, information gets through more slowly and less reliably. This is the mechanism behind the tip of the tongue phenomenon that intensifies in your 40s. The information is in there, the gateway is narrower. The anterior cingulate cortex governs emotional regulation, decision-making, and your ability to focus sustained attention. When its volume decreases, decisions that used to feel clear feel effortful. Emotional responses that you use to modulate easily feel harder to manage. The patience and clarity that used to come easily in complex situations requires more deliberate effort. The 4th change is not structural. It is biochemical. BDNF, brain-derived neurotrophic factor, the protein that drives the formation of new neural connections and the maintenance of existing ones, declines with age and with falling estrogen levels. John Rady at Harvard Medical School calls BDNF miracle-grow for the brain. When it declines, the rate at which your brain builds and maintains connections slows down. Learning feels harder. New information is less sticky. The brain's natural renovation process runs at a slower pace. And here is the part that makes this more urgent than most people realize. The Cambridge study found these changes were present in both groups of postmenopausal women, those who had used HRT and those who had not. HRT did not reverse the structural changes. The gray matter loss in the hippocampus and entorhinal cortex was measurable regardless. This is not a gap that hormone therapy fills. It is a biological transition that requires a completely different category of response. And the research on what that response looks like is specific, actionable, and almost nobody is talking about it. To understand why these changes happen, you need to understand the relationship between estrogen and the brain. Estrogen is not primarily a reproductive hormone. That is a reductive way to think about a molecule that has receptors throughout your brain, particularly concentrated in the hippocampus and prefrontal cortex. Estrogen directly supports the production of BDNF, the same neuroplasticity protein we just discussed. It modulates neurotransmitter systems, including serotonin, dopamine, and acetylcholine. It supports the integrity of myelin, the protective sheath around your nerve fibers that governs how fast signals travel between neurons. When estrogen levels begin their transition in perimenopause, all of these systems feel the change simultaneously. The myelin sheath becomes less efficiently maintained, which is why processing speed, How quickly you can move from thought to thought or task to task often feels slower. The neurotransmitter systems that estrogen modulated require recalibration. And BDNF production decreases, reducing the brain's natural renovation rate. Roberta Brinton at the University of Arizona has been researching estrogen's role in brain health for over 2 decades. Her work shows that estrogen acts as a neuroprotective agent during the reproductive years, and that the brain enters a transition state when that protection changes. Brinton describes this as the brain's strategic adaptation to a new hormonal environment, not a decline. An adaptation, but an adaptation that requires specific inputs to complete successfully. The key word in that description is inputs. The brain does not passively decline. It responds to what it is given. And the research on what it needs to make this transition well is some of the most encouraging science in this field. Here is what the decline narrative misses completely. The Cambridge MRI study found that gray matter loss in these regions was measurable in postmenopausal women. But the research also shows something the headlines consistently underreport. There is evidence of partial recovery and stabilization of gray matter volume after menopause in some individuals. The brain does not simply continue declining. In the right conditions, some of the volumetric changes stabilize and in some cases partially reverse. Kirk Erickson at the University of Pittsburgh, whose 2026 research used MRI data to show that exercise can make the brain look biologically younger, made a statement that should be at the center of every conversation about women's brain health after 40. He said, intervening in the 30s, 40s, and 50s gives us a head start, not in the 60s, not once symptoms are severe. Now, the window of intervention is not closing. You are in it. Think about a day in the last few years when your thinking felt completely clear. Not just functional, actually clear, where you followed a complex conversation without losing the thread, where you remembered details you thought you had forgotten, where decisions felt clean instead of effortful, where you sat down to do something and stayed with it without fighting yourself. Most women in their 40s can remember days like that. They just do not know why those days felt different. Now you do. Those were days when your brain had what it needed, when the inputs were right, when the BDNF was being produced, when the systems that estrogen used to regulate were being supported by something else. That clarity is not a memory of a younger brain. It is a preview of what a supported brain feels like at any age. Before the 3 fixes, a quick, honest question. Which of these 4 changes resonates most with what you have noticed in the last 2 to 3 years? 1. Memory retrieval is slower. Names, words, details take longer to come. 2. Processing speed feels different. Moving from one thing to the next requires more effort. 3. Emotional regulation feels harder. Responses that used to be automatic now require deliberate management. 4. New information is less sticky. Learning feels like it takes more repetition than it used to. Drop your number in the comments, because your number tells me which mechanism is most active for you right now, and it tells me what to focus on in the next video in this series. The most important thing to understand about every change described in this video is that none of them operate independently of inputs. Gray matter volume is not fixed. It fluctuates in response to demand, to physical activity, to sleep quality, and to cognitive challenge. Eleanor Maguire at University College London, whose landmark research showed that London taxi drivers had measurably larger posterior hippocampi than age-matched non-drivers, established something fundamental about the adult brain. It responds to what you ask of it at every age. The taxi drivers were not in their 20s. They were adults who kept asking their hippocampus to do demanding spatial work, and their hippocampus grew in response. BDNF production is not a fixed rate. It is stimulus-dependent. The most powerful stimulus for BDNF production in the adult brain is aerobic exercise. A 2025 systematic review in Frontiers in Aging Neuroscience confirmed that walking, running, and cycling all produce measurable increases in circulating BDNF levels. Erickson's own 2011 study showed that 1 year of moderate-intensity walking produced hippocampal volume increases in older adults. The entorhinal cortex gateway narrows under low-demand conditions and widens under learning and novelty conditions. The anterior cingulate cortex, the emotional regulation and decision-making region, is one of the most plastic brain structures in adults. Its function improves with the right practices. Every change this video described is real. And every one of them has a biological reversal mechanism that is equally real. Now, before the 3 fixes. 1 reframe that changes how you hear everything that follows. Your brain is not declining. Your brain is responding to the inputs it is receiving. If those inputs include high cortisol, poor sleep, low physical demand, and low cognitive novelty, then the brain responds by reducing investment in structures that are not being used. That is not failure. That is efficiency. And it means that changing the inputs changes the response. The brain you have at 50 is not the inevitable result of turning 50. It is the result of what you gave your brain to work with between 40 and 50. That is a completely different relationship with aging. And it is what the research supports. 3 specific inputs. Each one addresses a different mechanism. Each one has peer-reviewed research confirming its effect on the specific brain structures we discussed. Fix 1. Aerobic exercise for BDNF production. The 2025 Frontiers in Aging Neuroscience review confirmed that moderate aerobic exercise, walking, running, and cycling, produces measurable increases in BDNF levels in older adults. The specific protocol that produced hippocampal volume increases in Erickson's research was 50 minutes of moderate intensity walking 3 times per week for 1 year. Not intense, moderate, 3 times per week. The key is consistency and the heart rate elevation that drives BDNF release. One specific finding that most people do not know. The BDNF spike from exercise is highest in the 15 to 30 minutes immediately following a session. Research published in the Journal of Cognitive Neuroscience showed that cognitive training done immediately after exercise, while BDNF is at its peak, produces significantly better learning outcomes than cognitive training at any other time. If you are working on something that requires learning or memory, do it within 30 minutes of finishing a walk. Fix 2. Cognitive novelty for hippocampal demand. The hippocampus responds to spatial and navigational demand. The entorhinal cortex responds to novel information routing. Both structures can be directly stimulated through activities that require genuine novelty, learning something with no familiar framework, navigating new environments, and processing complex information without a shortcut available. Michael Merzenich at the University of California, San Francisco, who has spent decades researching neuroplasticity protocols in aging adults, is specific about what counts as novelty. It must be genuinely new, not a familiar task at a slightly higher difficulty. The brain adapts to patterns quickly. Once it has the pattern, the demand drops, and so does the neural growth signal. The stimulus for hippocampal maintenance is genuine novelty, regularly introduced. A new route, a new instrument, a new language, a new skill with no familiar analog. Fix 3. Sleep for gray matter preservation. Every structural change described in the Cambridge study was more pronounced in women who reported sleep disruption. This is not coincidental. Your glymphatic system, the brain's waste clearance network, runs primarily during slow-wave sleep. Beta amyloid, the protein associated with cognitive decline when it accumulates, is cleared during this stage. When sleep architecture is disrupted, particularly slow-wave sleep, beta amyloid accumulates faster and gray matter integrity degrades more quickly. The sleep and brain volume relationship goes further. Hippocampal gray matter volume has been directly associated with sleep quality in multiple studies. Protecting your slow-wave sleep is not optional maintenance. It is the most direct intervention available for the specific brain structures identified in the Cambridge study. Your deep sleep video in this series covers the full protocol for restoring slow-wave sleep. The link is in the description. If you have not watched it, this is the most important companion video in the series for your brain type. Here is what the research shows when these 3 inputs are consistently applied. Erickson's 2026 MRI data showed that regular exercise keeps the brain biologically younger. His exact words, "Intervening in the 30s, 40s, and 50s gives us a head start." Hippocampal volume increases have been documented in older adults after exercise interventions. Gray matter stabilization has been observed in postmenopausal women in the right conditions. BDNF levels increase measurably after each exercise session and improve baseline over time. None of this requires pharmaceutical intervention. None of it requires extreme lifestyle changes. It requires 3 specific inputs, consistently applied. The brain you have in 10 years is being built right now, by what you give it. Your brain is not declining because you are getting older. It is responding to the inputs it is receiving. Change the inputs. The brain responds. That is not hope. That is what the research shows. The Cambridge study mapped what happens. Erickson's research showed it can be slowed and partially reversed. Merzenich decades of work confirmed the mechanism is neuroplasticity operating at every age. Maguire's taxi drivers proved the adult brain grows when you give it a reason to. 4 changes, 3 fixes, all of it specific, all of it named, all of it backed by research that was done on real women, scanned in MRI machines, measured against controls. This is not a midlife wellness article telling you to drink more water and take vitamins. This is the neuroscience of what is happening in your brain right now and what the evidence says about changing it. Save this video. Share it with someone you love who has been noticing these changes and does not have a biological explanation for them yet. That explanation changes everything about how they relate to what they are experiencing. The next video in this series covers exactly why neuroplasticity does not decline after 40, even though everyone assumes it does. The conditions for it change. The capacity does not. That video is next. If you are not here to stay average, subscribe.